Last time we talked about how to represent the shape of an entire 3D object in one fell swoop. And the idea was that what you would want to do in practice is compare the shape of an entire 3D model, such as you would get after the processes of aligning and putting together multiple 3D data sets, and you want to compare multiple of those together for some reason. And I gave some examples of why you'd want to do that. For example, if you mock up a gadget that you want to put in a new object that you are assembling, and you have a database of similarly shaped objects that you want to select from. So now we're going to talk about the obvious other case where instead of trying to compare the shapes of entire filled-in complete 3D models to each other, you want to compare the shapes of not quite filled-in, not entire 3D objects to each other. So, just to review, there's a number of different ways to represent the shape of an entire 3D object, and you have to worry about different factors related to that, so invariances and ease of computation and robustness and so on. But let's talk about a slightly different application as a way of motivating the idea of just representing the shape of part of a 3D object as opposed to the entire thing all in one fell swoop. And the example application is going to be, well, instead of having full 3D models compared to full 3D models, we have scans of a scene. Or let's just say, for the sake of argument, one scan of a scene that has objects in it, and trying to find instances of objects that are in a database in that scene. So as you know from 3D surface sensing, you don't get to sense the interior of the object. You just get the occluding boundary of it that is facing the scanning device. So really you will only ever get to see part of the object that you are scanning in the scene. So you have a partial view of something that you are trying to compare to a complete view of something. And in particular, let's walk through the various different ways that global shape representations of the entire object, will not do very well at this problem of matching a partial view of something to a complete view of something. The first is what I've just been talking about, partial views. Let's say that we have our, I think we've seen this before, it's a 3D model of a little action figure. And if we were to scan that guy in a scene and we wanted to detect the fact that it was present in a scene, we might take a scan of it that looks like so. What I've done here is rotated this scan so that you can view it from a not very advantageous point of view. So basically it was viewed from the front, and this is a view of it from the side. So you can see there's no back, that part of the legs are missing, and parts of the underarm are missing, and so on. So this is just, even in a very, very simple scene where the only thing in the scene is the object of interest, there's still going to be the problem that basically half or more than half of the shape of the object is going to be missing when you scan it, no matter what position you scan it from. So in order to robustly detect that that particular object is in the scene, or basically that this model is the scene, your global shape representation needs to be robust to half of the shape going away. So in other words, if you have your vector of numbers, that is your global shape representation, and you get one vector of numbers from the full shape, the entirety of it, that's the model, and then you get your shape, your vector of numbers corresponding to half of it missing, that's the scene, they should be similar to each other. And generally speaking, they're not. Another problem, besides the fact that the front part of an object occludes the back part of the same object, other objects occlude each other. So if we have a scene that has two models in it, and these are basically a pelvis and the top part of your leg bone, that is the ball part of the ball and socket of your hip. If we have a scene like this where part of the hip is covering up part of the pelvis, then basically, besides the fact that you're only getting the front part of the pelvis in view, you're missing the part that is being occluded by the leg. So this kind of takes your problem of removing half or more than half of the shape data that is the object, and compounding it even further by removing more of the shape from the scene. And furthermore, if you take it from this point of view, it's not even the case that your pelvis bone is going to be one lump of points in the scene. It's actually going to be two disconnected things. So it's going to, in fact, appear like it's two separate objects when really it's just occluded by this thing in the middle. And not only that, but if these two things are close enough to each other, then your 3D sensor might not even be smart enough to figure out that they are, in fact, distinct objects. So it's very common to get data sets from 3D sensors that have one solid block of points that cover both this object and that one, which means that, in effect, you are going to go from comparing the shape signature or the global shape description of an entire pelvis to another entire pelvis, that's what we talked about on Wednesday, to now comparing the shape signature of an entire pelvis to the shape signature of a 25% pelvis, 25% leg bone. And if you think global shape descriptors or global shape signatures are going to be robust enough to that kind of variability, you have another thing coming. So this makes global shape descriptions completely change the numbers that you get in those feature vectors. So even going further and making the problem more difficult is what happens if we add clutter to the scene, where not only is, so I think in the previous example you could imagine there being a database that includes both models of pelvis bones and models of leg bones in them. So you would want to search for both of those things in the scene. Well, now imagine that the only thing you have in your database is ducky models, and there's all this other stuff in the scene that is not even in your database. And this is probably the most realistic kind of scenario for real-world applications. And in particular, imagine that you have a military type of application with radar that's downward pointed from an airplane, and you are trying to find certain models of tank in that 3D data set. Chances are that you are not just going to scan the tank and nothing else. You're also going to scan hills and buildings and foliage and maybe other vehicles and stuff that you have never seen before and that are not models in your database. So that's called clutter. Clutter is basically all the stuff that is not already in your database. So once again, we have made our problem of robust global shape descriptions even more complicated by saying that instead of having a shape description that is mostly or entirely the entirety of our object of interest, it's only part of our object of interest, and in fact it's mostly stuff that we haven't even seen before. And you can imagine that as the percentage of the scene that is filled up with your object of interest gets smaller and smaller, the problem turns in more and more and more to be like Where's Waldo, where you have a tiny little bit of something you're interested in that's embedded in a sea of garbage that you really don't care about. So if only 1% of the scene is taken up by your object of interest, that means 99% of your global shape description is going to be stuffed with junk. So that's going to make it completely different from what the global shape description of the model is going to be. So here's a slightly different problem. And it's basically an efficiency issue. So let's imagine that you have a database of 3D models of vehicles, and they include a variety of different pickup trucks, a variety of different minivans, and a variety of different sedans. Now, if you were to manually go into your 3D models and chop them into pieces and look at those pieces individually, you would notice that many of the back ends of many of the minivans look near identical to each other in terms of their shape characteristics. Similarly, if you were to take several different 3D models of several different sedan front ends, so for example from where the windshield stops forward, you would find that they look highly, highly similar to each other. So it should make sense that we should be able to harness this little bit of information. And so for example, you can imagine having one representation of an object that is basically a generic sedan front end. And you can imagine having a generic part that is, or a generic object that is basically the top half of pickup truck beds. So that means that if you have 50 different minivans in your database, instead of having 50 different back ends of your minivan stored all separately from each other, you have one minivan back end. And so instead of looking for 50 different types of things in the scene, you're only looking for one thing. So it's an efficiency issue. But now, global shape representations, the way I talked about it last time, basically take all of the shape characteristics of the entire minivan and lump them all together such that it's not always obvious how to decompose just the shape of the back end from the shape of the front end or the shape of the middle. With geons you can do that, but as I described to you, geons, practically speaking, are very difficult to use. So just using global shape descriptions, especially imagine a shape histogram. One of those things where you take the 3D shape and you convert it into a histogram. You can't look at the histogram and be able to say this part of the histogram corresponds to the front end of the minivan and this part corresponds to the back end. It's all kind of all gummed up together. So it's really difficult to do something smart about this idea of redundant parts, or in other words, segments of objects that appear multiple times in multiple versions of the same type of object. Any questions about these issues with global shape representations? All right. Another issue is has to do with what's called dense correspondences. So the way I talked about global shape representations last time, what you would do in practice, given two 3D shapes that are complete and filled in, is you're going to compare their shape signatures and then basically give a yay or nay decision as to whether they match each other. Now let's say instead you want a much more detailed sense of how well the objects match each other. And in particular you want what's called dense correspondences, which is to say a set of mappings from a position on the one surface to a position on the other surface. And so for example, let's imagine that what I want in the end is a description of the fact that this point on this object corresponds to this point in the scene. The reason why you might want that is for verification. If I have a set of correspondences between points here and points there, then I can determine what the transformation is that aligns this model to this scene, and then see how well it matches up. Basically get a goodness of fit between the object and the scene. And I can also do things like count up how many of those correspondences I have to get a sense of how confident I am that this object really is where I say it is. The way I talked about global shape representations, you can't really get this level of correspondence between objects, between two different 3D surfaces. Okay, so simply put, a local shape representation is going to be the opposite of a global shape representation, in that each local shape representation is going to represent the shape of part of your object of interest. And the way that this can help you for each one of these problems that I talked about is that for partial views, you basically have a set of local shape representations that cover just the part of the object that is being viewed in this scan of it. So if you're able to take, and those local shape representations should be robust in the sense that they're only supposed to cover the part of the object that is within view. And so if it's within view, they shouldn't be corrupted really. So if you can match those parts of the object to the analogous parts of the object in the database, then you have a good chance of matching them, even though you can only see part of the object in the scene. Occlusion, I mean, that same logic applies to occlusion as well, where if part of the object is covered up, then all you have to do is match the local shape representations that correspond to the part of the object that is within view. Clutter, same deal. Each of the little individual parts of the clutter are going to have their own local shape representation, and hopefully they don't match those of the corresponding, or those of parts of the object of interest. And then with redundant parts, if you have a similar type of part like minivan back end on multiple objects, then the local shape representation for that part of the object only needs to be represented once in your database. Or you can have a more compressed compact representation of the shape of that part of the object. Now, to get dense correspondences, what you can do is match local shape representation in the scene to local shape representation in your object model in your database. And what that'll do basically is tell you that this local shape representation matches with this one, aka this part of the object, this part of the scene corresponds to this part of the object. And in that sense, you can get local correspondences between parts of one surface and parts of the other. Does this make sense? Okay. So there are two general types of approaches to getting local shape representations for your object of interest. This is kind of your set of recipe slides. The first one, I mean, basically just to boil it down, you can either chop the surface up into non-overlapping parts, each of which has its own shape representation, or not. So in the first case, what you do is you have some algorithm that you have developed or that you appropriate that partitions the surface into non-overlapping chunks. So it takes your entire 3D surface model of a horse and it breaks it up and where each color corresponds to one of these chunks. Then what you do is you can calculate some numerical signature or set of shape characteristics that describes the shape property of each one of these patches individually without any reference to the other ones. So then, if you do that, then what would happen is you would do this for all of your models in your database, break them up into pieces, and get a numerical signature for each one of the pieces in the database. Then when you see a new scene, you would apply the same algorithm to break up the scene into these patches or chunks and get one numerical signature for each one of those chunks. So then you're back to the problem of comparing numerical signatures from the scene to numerical signatures from the object models. So if that's clear, then the downside to this approach should be clear right off the bat, which is that basically you have turned a problem that has one point of failure into a problem that has 2 points of failure. That is, you can either mess yourself up by failing to break the object into analogous chunks when you have the full object model and when you see it in the scene, or you can fail to match the patches to each other. Originally, we just had one problem, which was that our shape signatures might not be similar to each other across object and scene. Now we have those two things, because if it turns out that when you break your object model up into chunks, segment it like this, if you break up your object model and you into this many segments, and then when you image the horse in the scene, you break it up into this many segments, then you have a serious problem. You're not going to be able to find correspondences between the belly part and any one of these individual parts because this part has been broken up into several different parts in the scene. And by the way, this general problem of breaking a surface up into chunks is already itself a difficult problem. So now you've had the difficult problem of representing local shape properties and compounding it with another difficult problem, which is how to consistently and robustly segment a surface into chunks. Question?
Yeah. So when you segment, do you like you get like a here's the patches in the horse. Do you say the position of the patches relative to each other, or just like that it has these patches?
Well, what you would do is basically it's like the photograph segmentation case where you can't see them, but each one of these, but this and that, are made up of a set of points connected by edges. And what the segmentation problem is basically a mapping from points to labels. So this would be one label, this would be another label, this would be another label. So then that's the problem that is solved by the surface segmentation step. And so then what you would do is take each one of those labels, and now there'd be some set of points associated with it, and map that to a shape signature. So you do that for object and for all the objects in the database and for the scene. And you then compare the shape signature for each segment in the object, the set of objects, to the set of shape signatures for segments in the scene. Does that make sense? Okay.
Yeah.
Any other questions? Okay. So that's the downside of that approach. The other approach is called vertex-based, which is it takes the other route, which is to say, instead of representing the object in terms of non-overlapping parts, it represents the shape of the object highly redundantly in terms of a set of highly overlapping so-called parts. And in particular, what it does for each vertex on the object, it considers the shape of the neighborhood that surrounds it. So it would think of this green circle area as being one part of the object, and the red circle area as being another part of the object, even though they overlap with each other a lot. So you should see the downside to that already, which is that it's highly redundant. That it basically represents the shape of this portion of the surface twice in this shape signature for this guy and the shape signature for that guy. So it's highly, highly redundant. But for this reason, they tend to be pretty robust. You just have so much data that even if one of your local shape representations gets messed up, then there's probably going to be one adjacent to it that is looking pretty good. And also, it does away with this initial difficult problem of breaking up the object model into patches that are robust in some way, so that you always get the same mapping of the object to patches, no matter what point of view you view it from, and so on. So basically, you are creating opportunity for yourself by having so many local shape signatures. There's so many of them that you're bound to find a match between a shape signature for this object and a shape signature in the corresponding scene. Another issue here, though, is that I said that there is one shape signature per vertex or per point on your surface. So that means that if you change the resolution of the surface, make it more densely packed with a lot of points, or remove points to make it more space efficient, then that'll actually modify the number and distribution of shape signatures across the object. So you have to be careful about resolution when you take this kind of approach, actually. So this just kind of illustrates that point about robustness. Here we have our object model, and we have a view of it from the scene. It turns out that because the foot was covering up this part of the ankle, there's no data from this part of the ankle from this point of view that it was scanned from. So that seems like trouble, and especially if the shape representation for this guy had one shape representation for the entire lower leg, you can imagine that that shape representation would be kind of corrupted because part of the lower leg is missing. And indeed, if you try to build one of these local shape representations from this vertex here, it's not going to match its corresponding shape signature that's on the model because part of the shape information that went into it is missing. However, if you get away from that boundary, then basically every vertex that's far away from the boundary, for example here, is going to have a shape signature that should look corresponding or similar to its match over here. And that's, again, because it only takes into account a local patch of the surface when it's building up its shape representation. Any questions about this vertex-based approach? Okay. Yeah?
So the metric that you compute from the patch has to do with the curvature and a bunch of different...
Yeah, we'll talk about that. Yeah, and here you are. So now, depending on which one of those two approaches you take, you can calculate different types of shape signatures. And now, in a segmentation-based approach, imagine that you have your patch of the object that is shaped kind of like thus. Well, what you can do is think about that local patch of the surface as fitting some kind of a parametric model. And so, for example, you can imagine a local kind of curved part of that horse, where if you cut out that patch of the horse and look at it in 3D, it looks kind of like a parabola, or it looks kind of like a hyperbolic curve. And then simply what you do is you fit a parabolic or hyperbolic model to it, and then the shape signature for that part of the object is going to be the parameters of that hyperbolic or parabolic equation. Similarly, you can do what are called Bezier patches or splines or polynomial approximations to the shape of this thing. Remember we talked about splines where the idea was that to build an approximation of a curve, you have a set of control points, and then there's a curve that either goes exactly through all of those control points or gets close to the control points. And the idea is that the mathematical model gives you a formula for how to interpolate what the curve does in between the control points. Well, similar thing here, where the control points are actually going to be on the surface, and the parameters of your spline equation or of your Bezier curve equation are going to tell you what happens to the surface in between those control points. And the parameters of those spline equations are going to be your shape signature. So this is basically, if you were in statistics, this would be kind of very classical curve fitting, except in 3 dimensions. One problem here is non-uniqueness, which is to say, for each model, there might be many different parameter settings that fit the patch equally well. And if you go back to your parabolic-shaped surface patch just for a minute, if it looks like the top of a bell curve in terms of what the parabolic curve looks like, then you can rotate the thing about its center and get a different parameterization in the sense that x and y and z are in different directions, but they still equally well represent the shape of the object. So there's a non-uniqueness there. Or there's an ambiguity in terms of how it ought to be parameterized, which is a problem because in practice what could happen is that you can have two patches of the surface that are identical to each other, but they happened to get different parameterizations and therefore didn't match each other. Another problem is how distinctive are these parts of the object in any event, even if you are able to parameterize them uniquely. And so, if you have 10 different horses and you break up the horse leg into a cylinder and another cylinder, well, if they really are, honest to goodness, cylindrical, a cylinder looks like a cylinder looks like a cylinder. And so you won't be able to use just a simple cylinder to discriminate one horse from another from another. And the obvious problem is model selection. I told you that you can use splines, you can use parabolic curves, you can use hyperbolic curves to model these patches of your object that you have broken off from the rest of it. And so you have to pick one. And it's completely unclear which one of these models is sort of optimal for a given set of objects or for a given shape. And some of the questions here are, well, if you have a polynomial, what degree do you require? What degree of splines do you need? And again, anybody who is a statistician or who is active in statistics is very familiar with this problem. It's called model selection. Basically, if I have a set of data that seems like it should have a curve or a surface going through it, how do I pick the mathematical representation of that surface? And it's a vexing issue in statistics. Okay, any questions about segmentation-based approaches to these signatures? Okay, you should have gotten an announcement, or this was announced on SmartSite, that the midterm grades are posted. It worked out almost exactly the way I wanted it to, in that the mean was almost exactly 50% of the total number of points. So it's, in some sense, there's no portion of the class that is all squished in one end of the distribution. So it's great. And the standard deviation was 16. So again, rule of thumb, if you're within a standard deviation of the mean, you're probably doing OK. The homework 1 grades are posted also. And you should have, well, on Wednesday I told you that they're posted, but they weren't released. So now they're actually released so that you can look at them. One problem that is ongoing is that the SmartSite has a gradebook thing on it that allows you to look at your grades in a kind of a Flash or Java app kind of thing. And it insists on providing you with letter grades. You should completely ignore those letter grades because they're based on a rigid 90 to 100, 80 to 90, 70 to 80 scale that I am not going by at all. So in fact, almost everybody in the room will have grades that seem completely abysmal according to what gradebook is telling you, even if you're doing quite well. So this is a common thing that happens in this course, is that people freak out because gradebook is telling them that they're getting an F when they're totally not getting an F. Well, I mean, if you got 50% on your midterm, you're doing okay, and that's an F in gradebook. So don't worry about it. Ignore those letter grades. Any questions about administrative stuff? And obviously, homework 2 is out, and you should work on it early, the usual message. Okay? All right. Then let's move on. So what I've told you is that there's basically the alternative to chopping up the surface into patches and representing the shape of each patch is to have a kind of an egocentric point of view or a point-centric point of view, where in effect what you do is you imagine that the 3D surface is some kind of a topography. It's like a terrain that you're standing on. And you are standing at one point, and you are describing the world around you. You are describing the shape of the rest of the neighborhood of the object around you as you see it. And so you can imagine yourself with binoculars doing a 360-degree turn and describing the shape of everything that's around you, and then doing this for every point on the surface. And that's going to be your set of shape signatures for local shape for every position on the surface. So now the question is, using this metaphor, the question is, when you stand at one position and look around, what do you record? What kind of data do you extract about the shape of the hills and valleys that surround you as you are doing a 360 looking around you? One possibility is to use what are called curvature frames. Recall from an earlier lecture what the principal curvature is of a surface at a given point. The idea is that at our position on the surface, it's right here, we have a plane that goes through the surface normal there, because the surface normal is uniquely defined as being a direction that is orthogonal to the tangent plane there, which is also uniquely defined. And we have a pencil of planes. You don't have to know that term, but it's basically a set of planes that all go through the normal. And you can think about it as being a plane that goes through the normal, but it can be at any orientation with respect to the coordinates that you're in. But no matter what that plane is, it gives you a curve that is the intersection of that surface with the plane that you intersected it with. So that's the curve. And you can calculate the curvature of that curve, which is basically the instantaneous change in slope with respect to arc length. So it's how quickly the slope of that curve is changing as you walk away from that point. So now, and the principal curvatures are basically the maximum and minimum of those curvatures for all possible intersecting planes. So now you can imagine that the directions that the maximum and minimum of these curvatures are, that can be kind of a representation of, let's see, the direction that you have to go to change the fastest in terms of shape, and the direction that you'd have to go to change the least. So if you imagine if you are a saddle on a horse, so that there's the two directions that change quickly, which are the legs, and then the directions that go towards the head and the tail don't change very much at all. And where you sit down on the saddle, basically the part that changes the fastest would be in the leg direction, either of the leg directions. And the parts that change the slowest would be in the head and foot direction, because the curvatures really don't change at all. So the relative directions of the maximum and minimum of the principal curvatures can give you a sense of the local geometry of the surface. And you can imagine that being a reasonable shape signature for a surface point, Because in a sense, it gives you kind of the extrema of the geometry as you step away from your point of interest. Now, if you add surface noise on top of this, or levels of detail, you can imagine smoothing the surface using iterative Gaussian smoothing, which, as I've told you, if you do it long enough, it turns your highly complex, highly curvy surface into something that looks like a marshmallow. Iteratively removing detail as you smooth and smooth and smooth. So you can imagine calculating the directions of your maximum and minimum of your principal curvatures across scale in this sense. So you smooth once and you calculate the principal curvature, smooth again, calculate the principal curvatures again. So that'll give you a sense of how the geometry of the object seems to change as you change the scale or the level of detail. And these are called curvature frames. The reason it's called a frame is that, as you know, a coordinate frame basically is a set of 3 directions in 3 space. So our common one is the cardinal coordinate frame of x, y, and z axes all being orthogonal to each other. But you can also set up a coordinate frame that consists of the direction of the one principal curvature, the direction of the other principal curvature. They don't have to be orthogonal to each other. And then the third direction can be the surface normal. So then if you do that, you've basically set up a local coordinate frame that you can express other properties in, such as the curvature and how it changes with space. So these are called curvature frames. The problem with curvature frames is that they are inherently highly local. So basically, the principal curvature changes very, very quickly spatially. And it's only a valid approximation of the shape of the surface in a tiny, teeny, tiny neighborhood surrounding the point of interest. And if you try to represent the shape of this larger region like this with the curvature frames, you won't do a very good job. So if you go back to what we were talking about earlier, basically what this means is that your shape signature covers such a teeny tiny part of the surface that in your scene, you had better be lucky enough to sample the surface exactly at this location, or you're never going to find a match for it, because it only covers such a teeny tiny portion of the surface. And also, any descriptor that only uses a very teeny tiny part of the surface is probably not going to be very discriminating. Just as another kind of rule of thumb, if you have studied differential geometry, you know that one of the basic tenets is that every surface, if you look locally enough, looks like a plane. And that kind of rule of thumb should tell you that basically if your shape signature covers a small enough portion of the surface, then your shape signatures are going to look like planes too. So now you're going to try to match planes with planes, and planes in themselves are not discriminating at all, because every plane looks like every other plane in terms of its geometry. Here's the kind of next most complicated approach you can take, which is basically vertex histograms. So recall that what we're going to do is start at our point of interest. Here, call that x, and there's a surface normal direction n, and we are going to take our binoculars and do a 360-degree turn, and for each one of our rotation angles, try to say something about the topography of the surface around us. Well, one thing we can do, as we are doing our 360-degree turn around the object, is count how many surface points are a certain distance away from us. And I will call that alpha. So I will count how many points in the neighborhood around us are a distance between alpha and alpha plus delta alpha away. So this kind of band of distance away from us where I'm counting up how many points there are. And similarly, I also count how many points are a certain distance above me in elevation or below me in elevation. So how much higher above or below me in elevation, that's going to be beta. And there's going to be this band of elevation called delta beta that I care about. So if I do this for a set of alphas and a set of betas, then I'm basically partitioning all of the space around me into these cylindrical chunks. So each alpha with a delta alpha sized band is going to be a cylindrical shell. And then when you chop it up by beta, it's basically taking these infinitely long cylinders and breaking them up into discrete chunks. And then simply all I'm going to do is count up for every alpha beta pair how many points live at that distance from me and at that difference of elevation from me. So this is a vertex-based histogram. There's another kind of visualization of what this is doing, which I think is hopefully shown on the next slide. Do I have to? There we go. You can imagine that instead of having these cylindrical bins, what you do is you start with your point of interest and the surface normal, and you think about this thing as being like a fishing net. And what you do is you take a plane that goes through the surface normal and you spin it around, and as it's spinning around, it is catching the other surface points in the fishing net. And I think there's an animation of that, maybe, or maybe not. But it's illustrated here where you're spinning this plane around and it's catching the points as it is being spun around. And if you do that, you'll get exactly this two-dimensional histogram with a number of surface points for every alpha and beta. And this spinning idea is why these things are called spin images. And here's another graphical representation of that thing where you have some alpha, which is a distance away from you, and a beta, which is a change in elevation above or below you. And if you do this for two corresponding parts of the surface that have the same shape, you'll get a similar 2D histogram. And you can represent the histogram in terms of images, or they look like images, where darker means that there are more points at that alpha and beta away from you. And lighter means that there are fewer of them. Now, you will have to maybe take it on faith that this is an expressive and discriminating description of local shape. And it's also fairly robust to occlusions and clutter and so on, as shown by Johnson and Hebert. So, a couple of their properties. One is that they are rotation and translation invariant. The reason they're rotation invariant is because this coordinate frame of sorts, of alpha and beta, is set up with respect to the surface normal. So if you rotate the object, you change the surface normal, and that's it, really. So now the relative direction of where you go to get alpha and where you go to get beta doesn't change as you rotate the surface normal. It is a kind of complicated 3D to 2D projection. So we talked about the fact that to get a photograph, you take 3D surface data and you project it onto your CCD camera array. That's a relatively simple 3D to 2D projection that consists of taking objects in the world and mapping it onto a plane using straight rays that go into the rays of light that go into your camera. This is a more complicated spinning around kind of projection, but still it's a projection from a 3D thing to a 2D thing. And that means that they're not necessarily unique. You can have two different 3D things in the world that map to exactly the same two-dimensional description. So they're not unique. But if you think about it, that projection from 3D surfaces into your camera is not unique either. You can concoct different situations where different geometry or different surfaces in the world actually give rise to exactly the same image. One nice thing about them is that they look like images, and you can treat them like images. They're 2D. You can compress them using PCA. You can compare them. You can smooth them. You can do all the image processing types of things. I don't know, remove high frequencies from them if you so choose, using all the techniques we talked about in the first 3 weeks. Any questions about these? Yeah?
How closely do you have to sample, I guess, the points where you get these histograms to make them effective?
Yep. Yep. Absolutely. That's going to be on one of the next slides, but it's one of the engineering level design choices that you need to decide.
I mean, my mind thinks this is a grand idea and all. I mean, you would get paper, but how effective?
Yeah, this is exactly the engineering problem. And basically what has been shown to date is that there is a range of problems for which the person designing the system that solved that instance of the problem was able to find effective parameters for alpha and beta and delta alpha and delta beta. Beyond that, there are no firm theoretical guarantees as to how densely do you have, how many bins have to be in your histogram to make sure that you get something unique. Nobody has broached that theoretical problem, actually. A similar problem, or a similar approach, is what's called spherical histograms, where you take everything that I just said about cylindrical shells and you replace it with spherical shells. Spheres in 2D are circles, and that's what I can draw. So imagine that you have a 2D shape like this, and you break the world up into these spherical or circle-shaped rings that look like this, and you chop them up by angle. And so simply put, you just count up the number of points that fall into each one of these kind of piece of pie-shaped wedges, and use that as your representation of the object. Now let's see. We're not spinning we don't have cylindrical shaped bins, and this is actually a 3D thing. So points that are at different angles from you but the same distance get put into different bins. So it's actually a 3D thing. So you don't have this ambiguity of going from a 3D representation to a 2D representation. So that's good, but they're no longer invariant to surface rotation. And that should be obvious because what happens is if you rotate the letter A, all the points end up in different bins, and you don't really have a good mechanism for determining what the sort of zero bin should be, or in other words, rotating the entire set of spherical bins to go with it. These are called shape contexts, especially in 2D is what they're referred to. So there's a set of engineering issues which we have just started to broach. One of them is called spatial support, which is to say, how much of space should this histogram cover in order to make sure that your description of the object is distinctive, but not overkill. So if it covers too small amount of space, like this one, for example, then like I said, if you only look at a very small neighborhood around you, everybody looks like the same thing. They all look planar. Meanwhile, if you cover too much of space, then clutter can insert itself into your shape histogram. And in particular, if your object is sitting next to a pelvis over here, then a lot of your shape signature is going to be made up of pelvis points as opposed to rubber ducky points. So as engineers, we try to hit the sweet spot of including enough shape information that we have a high probability of getting a distinctive shape signature, while at the same time not making them so big that we include lots of clutter into every shape representation. Spatial support. Now, I think this is what we were just describing before we got here, was how many bins do you need in your histogram? If there's too many, then you get something that looks like this. It's highly computation intensive, and they're not very, very robust, in the sense that if you jitter the surface a little bit, all the points will jump into entirely different bins. If you set the number of bins in your histogram too low, then everything starts to look like everything else. And every part of the surface has the same shape as every other part of the surface, which is clearly not what you want. So again, Mr. and Mrs. Engineer have to put on their engineering hat and find the parameter setting that gives you kind of a sweet spot where you are robust and you have a good amount of shape information but not too much. So there are pros and cons to the fact that spin images are rotation invariant. On one hand, if you have the same object and every part of the object is distinct, you would want to detect the fact that you see a part of it in the scene even though it is relatively rotated with respect to your model in your database. However, if it's invariant to rotation, that means that corresponding positions on the left side of the ducky face, like this one, look exactly like points on the right side of the ducky face. And that means that when you compare these spin images, there's always a kludgy part afterwards. We have to disentangle the fact that the left side of the face seems to be a really good match. This left side of the face in the model seems to be a really good match to both the left and right sides of the face in the scene. And in fact, if you do that poorly, you might end up with a flipped match where all of the left side of the ducky matches all of the right side of it in the scene. So that is the pro and con of invariances in these shape signatures. And there's a similar kind of thing for spherical histograms as well. So just to summarize, local shape representations can be helpful for dealing with occlusion, partial views of an object, clutter, finding dense correspondences, and for dealing with the fact that some objects have redundant parts if they are in the same category. Segmentation-based approaches chop up the object into discrete segments, and vertex-based approaches represent the neighborhood surrounding each surface point so that they are highly redundant. Any last-minute questions? Okay, see you next week.